is in general about new ideas, new developments in the electron ion collider related science. And now we'll talk about mass structure and pressure forces inside the nucleon. So Luke is going to give the theoretical overview.
Right, good morning, and first of all, I'd like to thank the organizer for having me here. And today we talk about the mass structure and pressure forces inside the nucleon, which are essentially based on a paper on arXiv and then published this year on the mass decomposition. And the recent work that we just completed and that will appear this week on arXiv. I'm particularly excited about it because it has been already for 6 years I've been thinking about this kind of idea, so it's good that at the end it came out. So the structure is the following. Just a few words of introduction, but I will be very quick because you all know that, and then focus on the main object of interest, which is the energy momentum tensor inside the nucleon. And I will review the different mass decomposition because these are the objects that I used to say that so much of the proton mass comes from quarks or gluons, and we see depending on the decomposition you take, you have different pictures. And then I'll move to a special distribution of these quantities, especially review in detail the 3D distribution. I won't talk about the 2D, but in the paper I mentioned, we also developed the 2D relativistic distribution of energy and pressure. And then the last bullet would be naive comparison with what we have in the case of neutron stars, to see that maybe we can say something or learn from neutron stars. But we'll see this later. So basically, we have basically two pictures of the nucleon, whether you look at low energy or high energy. Low energy, we think of your nucleon is made of constituent quarks, massive quarks, and the total mass of the system is essentially the sum of the constituents with a little bit of binding energy that would be negative, and the orbital angle, the angular momentum of the system would be essentially the sum of the quark spin, or the constituent quark spin. When you look at high energy, where people looked essentially at the quark spin contribution, you are having a completely different picture where you don't have only three massive constituent quarks, but a whole bunch of quarks, gluons, which are almost massive. And there, in that situation, relativistic effects are very important. And so this is basically the situation we have now concerning the mass and the spin decomposition. So for the spin decomposition, we know that about a third or quarter of the nucleon spin comes from the quark parts. Gluons can be as large as 40%, still large error bars, and totally unknown is the orbital dynamic distribution, which is really hard to access, but that would be one of the main goals. Concerning the mass, we know pretty well, this is for the G decomposition, the quark kinetic energy, the quark mass contribution, and what is not known essentially is the part that comes from gluons and the anomaly. We can infer that using some rules, but we haven't measured that yet directly, and Zainadine will develop more in that situation. So when we say that 1 or 2% of the nucleon mass comes from quarks and the rest is gluons, that's a very naive picture where we take three current quarks inside the nucleon, and then we say that okay, you just add the current mass of the three quarks, and then you end up with 1 or 2%. So if you want already a little bit more realistic picture, we have actually a condensate of quarks inside the nucleon, and plug the number, when you get about 13% that will come from the quark mass, so the part that is generated through the Higgs mechanism, and the condensate from the QCD, and the rest, well, is essentially the rest of the dynamics that is coming from QCD. Well, we have seen already this many times, that we know that the US National Academy of Sciences recognized that the question of the origin of the nucleon mass and nucleon spin are really key questions that we want to address with the EIC. And recently, there's been the first experimental instruction of the pressure distribution from data at JLab, showing that, okay, that analysis, the point that maybe the pressure would be 10 times larger than what is found in some neutron stars. Still some works are going in that direction. So the thing is, whenever you want to speak about the nucleon mass, spin, and pressure, all these concepts are related to one unique object, which is the energy momentum tensor. That's why I was interested in that object, and I think that's the natural object to gather many people in different fields and different aspects of the nucleon
momentum tensor is sort of a complicated object because it's clear that it's fully characterized by its pressure and energy density.
Yeah, you can. So if you look at for stable systems, so you're not looking at just the eligible to tensor, you're looking at the matrix element eligible to tensor in a stable system. That's what we are going to do. And that one would be enough to talk about pressure and energy contribution to different quarks and muon contributions. Now, exactly how to define them in a unique way and how to relate to experiments, that's the subject of the discussions. So the energy momentum tensors, this kind of big table where you learn about the energy density, momentum density, flux, forces, pressure. And as you know, this object is used in many, many different fields, quantum plasma, hydrodynamics, the structure of stars, cosmology, and so on. So it's a natural object if you want to convey the physics you are doing with the nucleon to other communities. So that's why I think it's very nice to focus on that guy here. So, in order to study the energy momentum tensor, we're not studying in the most generic case. What we are interested in is to look at the energy and mass distribution inside the state, a stable state. So, if you take a hadron with spin 1/2, and you take the matrix elements for within the state for the QCD energy momentum tensor, or any energy momentum tensor in general, you can decompose into a certain number of structures, Lorentz structure. That would be Lorentz scalars that are called energy momentum tensor form factors or gravitational form factors. So you have 5 of them if you consider the most generic case for local gauge invariant operator. So you get the part that is essentially associated with the momentum, and we know the energy momentum tensor is of course related to the form momentum. It's a spin rank 2 tensor, so you have spin 2, so you get also this kind of structure. Since we have a target that has spin 1/2, we have an extra structure, which is this one. We're also considering a target where the constituent themselves have spins, the quarks and the gluon have spin. So in general, the energy momentum tensor should not be symmetric. So we have an anti-symmetric part that comes here. And the last term is that when you consider separately the quark and the gluon contribution, then the separate contribution are not conserved. There is an extra term that accounts for this non-conservation. So all the information that we're interested in is encoded in those 5 functions. Of course,
what is this last term?
So the last term is, so that one is the only one that would be responsible for an anti-symmetric contribution to energy momentum tensor. So if you look, in general relativity, you assume the energy momentum tensor is symmetric. It's related that in general relativity, they are not considering intrinsic angular momentum. So if you do field theory with intrinsic angular momentum, you have an intrinsic spin tensor. You impose a conservation of total angular momentum, and you observe a relation which is the anti-symmetric part of the energy momentum tensor is given by the divergence of the intrinsic spin tensor. And what can be shown essentially is that the form factor here is essentially minus the isoscalar axial charge, the spin of the quark.
But the notation is confusing because D is open.
Well, this is the G. This one appeared way before Maxim Polyakov. And Maxim Polyakov wanted to call D divided by 4, call it D. But okay, it's just notation. This is actually all the stuff that came back actually to the paper here.
So this term doesn't couple to gravitons.
It doesn't couple to ordinary gravity, but if you look to Einstein-Cartan theory, it would couple to Einstein-Cartan theory where torsion.
So this can be also written in terms of all the landscape.
You can make a relation to the poly.
So you have this picture that curved space has precession in the background. So that in that way.
Exactly.
So it's the gyromagnetic moment.
Exactly. And also now, since we know that we can measure gravitational waves, so people are looking polarization effects related to the gravitational waves, and so that's why people are again interested in the question whether there could be torsion or not in actual gravity. So our states are on shell, which is given by this relation that we can re-express in terms of the average for momentum, which I keep here, and the momentum transfer given here, whose square is t. So we can relate p, the mass, and t. And also that the average momentum is orthogonal to the momentum transfer. P is time length, so basically in interpretation of those matrix elements, it gives you in which frame you are making the interpretation. And the full momentum is a full space-like vector. It contains information about the spatial distribution inside the state. So in quantum chromodynamics, we know the structure of the classical electricity energy momentum tensor, which I give here, and I do not symmetrize over the indices here. And of course, in the quantum field theory, you have to consider the renormalized field, and we know that the trace of the QC energy momentum tensor is anomalous part. We have the trace anomaly, pure Gluon part, and then you have the quark part, which is the class 1 plus the quark anomalous dimension here. So things which are very well known. And you have also constraints that come from Lorce invariance, which is, and translation invariance. So translation invariance tells you that the energy momentum tensor is conserved. And from that, you have the momentum sum rule and the stability constraint, which is that one. And conservation of total angular momentum. So you see you have a part which is purely orbital plus the intrinsic angular momentum. From that, you obtain that the sum is factor B at t equal to 0. So this is related to the equivalence principle. If you have the equivalence in gravitation. And then what I mentioned, that the anti-symmetric part of the energy momentum tensor is directly related to the spin of the constituents. So this is what we can do totally in general. So the first thing is that we are considering the forward matrix elements. So the forward matrix element gives you the information average over all space. And as Alf has already shown, that if you look at the forward matrix element of the total energy momentum tensor, it has to take this form if you assume a relativistic normalization of the state. And if you take the trace of that expression, then what you observe, that's essentially on the left-hand side, right-hand side here, you have the mass of the system, and on the right-hand side, the trace. And then you insert the expression for the trace, where you can say, okay, that would be my gluon part, and that would be my quark part. In the information we know about this, the condensate based on experiments and lattice QCD, you get about 11%. And for the sum rule to be satisfied, you infer that the gluon part here would be 89%. Well, let me then provide some discussion of that. Essentially, it's very nice in the sense that it's apparently fully covariant. It's also compatible with the Gell-Mann-Oaks-Rayner formula from carrier perturbation theory, because if you're considering a time state, this part would be 0, then you're only related linearly to the mass, current quark mass of the quark. But still, there are problems that are usually not mentioned. The first thing is you can see here is that this is true only if you use this normalization of the states. If you use another normalization, and you can do it, we know in quantum mechanics you can use any normalization provided that you consider the properly normalized expectation values. The physical result should not depend on the way you normalize the states. So here, this interpretation is already based on a particular choice of the normalization. So it's not so nice. So you're also sensitive to the energy momentum tensor at a single point. You think that the nucleon is extended. So what is the connection with knowing the proton at one point and the distribution of energy and mass? And also we are looking at the trace of the energy momentum tensor. And we know the trace contains the energy, but also part of the spatial part of the stress part of the energy momentum tensor. So it has no clear connection to energy. So this relation is based at the level of the matrix element, but it's not based at the level of the operator. So if you look at the operator itself, how can you say that, oh, that's the quark mass, the gluon contribution to energy? You can't say that. You infer that only at the level of the matrix element. And I can imagine lots of matrix elements which are proportional to the mass, and still they do not mean that they correspond to the quark contribution. So we have to be careful with the use of such a formula.
Are there any problems also with P plus equals 0 modes? Ordinarily, when you do condensate, you find there's a contribution with constant P plus exactly equal to 0, and that you won't get by looking at distributions.
Yes. So
is there a problem?
Yes, it could be a sort of problem, but instead to work in more this direction.
I mean, at this point, you haven't made any assumption about light front or anything.
No. Just saying, if you do so, that's what you, and that's the thing that you can find many papers, old and also recent papers. That's a
Well, but I
picture.
think you have once you put numbers beneath the number. You made an assumption when you put numbers down there. Right?
11%.
Then that come from looking at structure functions and stuff.
So these numbers are inferred from the pi nucleon sigma term, and then also you use to have an idea for this stretch quark condensate. You use the lattice calculation. So there's some phenomenology behind, but that was just to give a rough idea of the number we may expect from that. From that picture, people would say that the proton mass is essentially coming from gluons and a little bit from quarks.
On the previous slide, and then we had
The what?
on the previous slide, when we had that one, or whatever, previous.
Yeah.
Whatever. Yeah.
All right. So G.
Before you move on, so I'm not sure I understand the concern about spatial extension. So certainly T mu is a local operator, but your P states are momental space states, and they include integration over the whole space.
Yeah.
So yes, you're probing energy density at one point, but your proton is not fixed in the way you kind of move the proton all over the space. So you are probing in on tails and everything.
Totally agree. And so you have a state which is totally delocalized, and you look at the normalization of that state, you get delta of 0. So you have divergence, and then you have to compensate for, if you want to really think of this as an actual density, you have to divide by P, that you get the state P, normalization of the state, and that you get.
But that's a normal field theoretical procedure, you put it all.
Yeah, but then how do you solve that? By hand, by say, oh, I'm not understood the normalization, this is not really satisfying. But you can do it like this, but that's by hand. You have a normalization factor, which is formally infinite. And a way to get rid of that I can show you later another time is using the Wigner representation of what is the state at rest and moving strong. That will be for this. But you can solve that part in a more clean way than what is unusual. So G proposed another decomposition where, because he wanted really to relate to the energy density, so the T00 component of the energy momentum tensor. So what he did first is to decompose the energy momentum tensor into a traceless and pure trace part, and the traceless into a so-called quark and gluon contribution, and the trace part into the terms we have already seen, the quark part and the trace anomaly. And then you can parameterize the forward matrix element of T mu for both the traceless and the trace parts. And if you write this notation in terms of the, let's say, the more modern notation in terms of gravitational factors, these are the combination you obtain. And then you define the contribution to the T00 is essentially the energy momentum tensor defined at point R. You integrate over all space. You take the matrix elements in the state with given momentum P, and you divide by the normalization of that state. That thing is really well defined. It doesn't diverge. You do not have to put by hand infinite normalization factor, because essentially the integration over R gives you an infinite delta of 0, which cancels by the delta of 0.
So why didn't you do it on the previous page? I mean, that's simply the normal procedure.
Yeah, but people don't do that, because if they do that, well, they could do that, but then they will have people who want integration of a D3R, and if you integrate with D3R, you lose explicit covariance. So they don't like to do it. So they want to preserve Lorentz covariance and having the connection to the mass. So G said, okay, I'm not so strict on having explicit Lorentz invariance. Let's say I can go to a certain frame and say that the mass of the system is simply the energy in the rest frame of the system, and then I decompose my energy. And this energy decomposition, I call it the mass decomposition of the nucleon. And if you do so, so G obtained then decomposition into 4 contributions, which are essentially related to the 0,0 component of the traceless and the trace part. He had a little bit of reshuffling, but okay, to some extent. And then, again, using the numbers we know previously, plus the momentum fraction carried by quarks and gluon individually, so give an idea of what are the numbers for the different contributions.
So how does this really distinct from just computing Hamiltonian right now? There's decompositions.
So if you use light from, you won't use a 0,0 component, you will take a plus minus component, which is a different object. and the decomposition will be different because you're already looking at different component energy momentum tensor. So here it's the instant form, and I will in this talk only focus on the instant form. If you're interested in the light front, I refer to the paper I mentioned, which will appear tomorrow, the day after tomorrow. So now we have a proper way of normalizing stuff, so everything is clear. We have a clear relation to the energy because we're looking at the 0-0 components. Well, the problem is that, okay, not really a problem, but we have to accept it that whenever you talk about quarks and gluons separately, there will be in general a scale dependence, and maybe the big argument that people will use against G decompositions, that's it's done in the rest. Some people are not happy with that, but okay, that's it. And another point I will add is that especially since you are focusing on the 0-0 component and you do a lot of manipulations, you are not looking at the other components in the energy momentum tensor, and actually you are mixing your energy densities with pressure effects. So what you call the quark energy, etc., may be actually a combination of the actual energy plus pressure effects. So to recover the covariance that's still related to the 0-0 component of the energy density, well, first you look at the energy momentum tensor separately for quarks and gluons, and you see that you have two contributions. So again, you get the general gravitational form factors A and C as before. And if you look here, then recognize the structure which is very similar to the perfect fluid energy momentum tensor. So be careful. I'm not saying that quarks and gluons inside the nucleon form a perfect fluid. I'm just saying that if you look at the structure of the corresponding energy momentum tensor, it is similar. So this allows me to identify a certain combination of the gravitational form factors with what is called the proper energy density and the proper pressure inside the system. So if you do so, then that case would be for a system where the form velocity is essentially the form momentum divided by the mass of the system, then you can relate the energy density as this combination and the pressure as this combination. So since we are looking at the forward matrix elements, this corresponds to an average over the whole volume of the nucleon. And then you can define the total energy as essentially the density of energy multiplied by the volume, the proper volume of the state. And actually you don't get one sum rule, but actually you get two sums. When you look at the full energy momentum tensor, you have a mass decomposition into only quark and gluon parts, which are essentially almost 50-50, like the momentum decomposition. And then you have another sum rule, which is essentially describing or implementing the stability of the system, especially that the pressure volume work, the pressure of the quarks must be exactly compensated by the pressure of the gluons. There's a system where the total pressure should be zero, otherwise either the system will collapse or blow up.
So I'm sorry, I'm kind of lost.
Yes.
In one of your earlier slides, you had a lot more terms with this anti-symmetry term. Why
Yes.
don't you have that?
Well, if you look at the forward matrix element of this, you set delta equal to 0. So this is 0, this is 0, this is 0. The left is 0. The other ones are interesting when you look at the spatial distribution that will be the second part.
Okay. And now when you look at this element, you're not dividing by the PP state.
So when I'm doing this thing, you can also divide with dividing by the PP state, and you get exactly the correspondence. Because when you make the correspondence, that's where you have to be careful with dividing the PP states. But this is included. So what I'm considering and defining the actual energy densities and pressure, I have also to do something with this detail. So again, this is more technical detail. You can also look in the mass decomposition paper where I explain this too.
So I have a question, sir.
Yes.
When you have the R, the integration over R,
Yes.
that R is not the same as the conjugate to P, like the conjugate to...
Yeah, that's a conjugate to delta.
It is?
It is.
Okay.
And integration over R means delta equal to 0. That's why you have 4 matrix elements.
But I'm sorry, I mean, maybe it's a naive question. If you go back, yeah, you can write your O of R
Yes.
as O of 0 with the exponentials into the IPR, into negative IPR,
Yes.
which cancel each other after acting on the states, and R dependence is gone. So you're really multiplying everything by infinite volume.
Exactly. Which is compensated by the infinite value that
It shouldn't be, right? If you're always a unit operator, your average of a unit operator will be the infinite volume, right?
Not if you properly normalized. But if you have the unit operator, the denominator and the numerator, you get P identity P divided by PP.
Yeah, times D3R.
If you integrate over D3R, yes, you get the
Put O to be a unit operator. The expectation value of a unit operator then will be 1. If I use the prescription on the right hand side, I'll just get the volume.
yes.
That sounds good.
So O here, so if you put the operator, that's the distribution of the quantity you're interested over space. So what you are considering, of course, is the
Also,
volume integral.
OR is not an operator, it's a density.
It's a
So
density
the
in
unit
the
operator
position.
will be 1 over
Exactly.
volume.
Like when you take T mu nu of X or R,
But
T mu nu is the density in R.
otherwise the dimensions would work.
Well, for expectation value of 1 would be volume.
Cedric, yes, last curiosity. The second condition you get there, so the equilibrium between the pressure, means that this is the condition to have a stable system. Otherwise, you said it collapses or it blows up. Is there a relation between this condition and the confinement?
That's an open question. So that's why getting our hands to the C-bar form factor, which is related to pressure, maybe gives some hints about confining features. I cannot say it is confined, but there's
Actually, the condition is more general because
yes.
You could blow up, but you could also collapse. So it's not clear where confinement fits in this picture. But certainly the stability should be related.
At least the spatial distribution. You say something not that equal to 0 because you integrate over all space. If you consider a star, we have no confinement as forces. But the spatial distribution of C-bar can maybe tell you something about confinement.
You could say something about susceptibilities, right? So derivatives of the pressure.
Yes, exactly.
But if you look at, say, that would involve looking at correlator. So,
one of the problems is it's not a homogeneous system, right?
It's not a homogeneous system. So that's why here it's still averaged. And then now we go differential and we see
pressures in inhomogeneous systems where the scale of spatial gradients is of the order of the same size scale as the inverse momentum of the systems.
yeah, I will show it a little bit later. Yeah, go to that direction. So the main message here is essentially that if you want to keep things covariant, it still relates clearly to energy, the concept of energy, while you get only decomposition, unique and ambiguous decomposition to quarks and gluons. Why G at 4 terms is essentially because he combined artificially, because he didn't see it, because he considered a non-covariant approach, the pressure effects with the terms. So you have 1, 2, 3, 4, and you got 4 terms. So here's the summary of the 3 decomposition. The trace G, and it's the one I propose. Essentially, if you sum the quark parts with the quark mass term, that would be the total quark contribution. And the 2 decomposition of the energy and the pressure are in principle independent. But if you combine these 2 information, you can create a decomposition into 4 terms, which means that if you try to find the equivalent pressure volume or stability constraint with G decomposition, you learn nothing new because the information is already encoded into the decomposition into 4 parts. So also why I would push for using such a decomposition is the one that you can also relate to the work of Maxim Polyakov, where we discussed that the pressure distribution and energy distribution inside the nucleon. That's the one that is related to one. There is no connection to G's decomposition in this case. So far I'm looking at the 4 matrix elements. So if you want to look at the spatial distribution, we have to look at the T dependence of the form factors. So I will discuss here only the 3-dimensional distribution in the bright frame, where still some relativistic correction that apart from these. The main point is if you're looking at the initial state and final state, and if they are with different momentum or energy, well, they will suffer different Lorentz contraction factor naively. So if you are interested in density, the minimum requirement is that you have the same Lorentz contraction, which means that you must have the same boost factor. And this is achieved if you go to the bright frame. But in the bright frame, only the modulus of the momentum is the same, and only the direction changes. So if you look at the average 3 momentum of the nucleon, it is 0. So even though you have a nucleon that's moving in the initial and final state, in average it is 0, and then we say that we are looking at the distribution inside a nucleon, which in average is at rest. That's the idea of the bright frame.
So that then you come up to this age-old problem, right, which is what happens with boost operator, like Newtonian.
Yes. So the three-dimensional distribution we get usually are not the truly relativistic one, but these are the natural one that you can connect to the non-relativistic distribution. So if you take the three-dimensional picture as modulo relativistic corrections, it's fine to work with them, and that's the one you can connect to non-relativistic quantum mechanics. If you don't like it at all, you can work with the two-dimensional one using the infinite momentum frame or the light frame picture, but I won't show them here. But basically, what we show is that what you get for most of them is the same as the bright frame integrated over the z direction, which is very nice.
That's not obvious at all because these p plus zero.
So definitely have much more things to look at this particular configuration. The connection can be made. So if you look at the bright frame, you have no energy transfer in the system. That's really one of the important criteria. And you can then define the three-dimensional Fourier transform as this kind of objects that people write from the beginning without explaining where it comes from. So if you look at the matrix element of the Hegemonic tensor in the bright frame, then you see that essentially that's what you get. You see that there is no d term. We assume essentially we consider the unpolarized configuration to simplify a little bit. So we have no d term here. Essentially, you have otherwise all the other form factors. And then you have to consider the three-dimensional Fourier transform of this guy. So with the trained eye, you will recognize essentially this looks like the four-velocity at rest. Then you have the metric, and then you have a space-like vector that's given here. So by Fourier transform, you will have a structure which is exactly that one, and which is the one used to describe anisotropic fluids. That's the kind of type of matter somehow that is used, for example, to describe neutron stars. So what happens is you have now the energy density, but you have tangential pressure and radial pressure. So if you are considering a spherically symmetric system, there is no reason why the stress of the stress should be isotropic. All you know is that essentially you have a stress in the radial direction using the spherical coordinates that can be different from the tangential one. That's something that is known for a very long time. Already Einstein noticed that. That's why people now in Neutron star physics and also for modification of general relativity are more and more interested in this kind of space-time or sometimes also matter distributions where tangential and radial pressure are different. You can relate the radial and tangential to the ordinary isotropic pressure, and the difference between the radial and tangential is called the pressure anisotropy. And that's what Polyakov called the shear forces. So in order to have an idea of the shape, so we have worked out the explicit expression of to write, for example, the energy density, the pressure here, in terms of those form factors, the Fourier transform of those form factors. All these are in the paper I mentioned. Here I would just like to show, to get a feeling of how this distribution can look like. For that, we use a simple multiple model. Essentially, we took a dipole model for most of the form factors. And for B and C, we use a tripole form factor, which is consistent with the positivity of energy and quantic groups at large T. And so here I show the energy distribution inside the proton for the total, which is given here, and separately for quark in dots and dashed quickly for gluons. So we clearly see that the energy density is everywhere positive. And if you multiply by r squared, then this gives you the radial. So if you integrate over dr, that would be the density already including the spherical volume. So you clearly have positive numbers everywhere. Then you can also estimate with this simple model, which is based on lattice information we have so far and some partial experimental numbers. we can estimate the average square radius for the mass. Thank you. Which is about 0.9 Fermi, which is a reasonable number, and slightly larger than the charge radius we know either from the unique hydrogen or the standard hydrogen or electron proton scattering experiments. So this seems reasonable, and I think it's very interesting to compare how the energy inside the proton is distributed compared to the charge, because we see whether who is carrying the charge inside the system. Then we can also look at the pressure. So here I'm showing the radial pressure, again for total quark parts and gluon parts. And then what we see is that essentially the radial pressure is everywhere positive. But that also makes sense if you think of your proton as essentially shells which are pushing each other, then the radial pressure should be always positive. That's also what is known in neutron stars.
So we've done a similar study, and so we used the form factors calculated by Travis. So there's a recent paper by Edmond and Shanahan, which calculates the gluon form factors. So this is basically the conjugate of the beta. It's not the conjugate, the Fourier transform of the.
So that's the black one, yes. The dotted in the dash, not, because it contains also a contribution from the C bar.
Yeah, okay, so for now we are not looking at C bar, but so what we find is that the gluon contribution is actually very high compared to the quarks, which is, I mean, and that's not really what we find, it's basically.
Well, because you don't have the C bar, and the C bar is very important because it changes a lot the contribution you will attribute to quarks and gluons separately. So as soon as you want to talk about quarks and gluons separately, you cannot discard the C bar form factor. And that contribution is very important and can overcome to a big extent the contribution from the C alone, or the C form factor.
Yeah, well, that's sort of the question: is how do you break apart the quarks from the gluons as they interact with one another?
Yeah, so they interact, so they exchange. But what we are looking at
I mean,
are
there's a term A side or psi, right?
yes.
And that one can't be thought of as either gluon or.
Cybars, okay. The way first there is a thing how you define separately the quark energy momentum tensor from the gluon energy momentum tensor. There's also been a recent paper by Abba.
Let me ask you this is a principal question. I mean, how do you identify a psi bar psi as either gluonic or quark?
So psi bar psi, I define it as a quark. That's a choice.
But do you have an A there? You have a vector potential there.
Ah, okay, you mean for the three, okay, that's the A.
You have interacting,
He's referring to a different A.
Yeah, okay, sorry. I thought you were talking about the gravitational factor. No, okay, for that one, so that's the one that comes from the covariant derivative. So I'm looking at local operator like G. I define that as a quark for the kinetic energy. But of course, you have the freedom to say, okay, I can attribute using the equation of motion to a part of the gluon part. But for that to make sense, we will have to use non-local energy momentum tensor. So that would be canonical, like for the angular momentum. Things becomes more complicated.
So that may be part of the issue. So how you define it.
Yeah, so I mean, to sort of ask a
Yes.
variant of that question. I mean, so suppose I imagine going to very high energy limit,
okay,
radial limit, and there you can pick up these quark and gluon fields as classical fields,
okay,
or especially gluons, and you can say the pressure is given by the pressure of these classical gluon fields. That's pretty dominates. It's much larger than these.
and your picture holds in no X.
Yeah, so low X, yeah. So
and here it's integrated.
that's also the mass.
Here it's integrated over X.
Yeah, but if it's an unpolarized proton, that's as much the pressure of the proton as this is. So how would you say that? Because again, if you work in a Lorce environment, that is the proton.
See, part of the issue is sort of these whole momentum sum rules where you have about half the momentum of the proton listen gluons and half listen.
So that's why from the beginning you have to identify, say from the very beginning, that combination of that operator, I call it the quark contribution, that operator, I call it the gluon contribution. That's something we fixed beforehand. people can make different choices, like the Jaffe-Manoir angular momentum and the G angular momentum. Once you have specified it from the very beginning, it's clear what you mean. You might not be happy with it, with that operator being called quark congruence, but at least you have defined it and you can measure it. So in this sense, I'm using here really the same definition as G for the quark and gluon contribution. So the radial pressure is always positive. If you look at the tangential pressure, you have a sign change. So essentially, you have a repulsive force near the center, attractive force at a larger distance. What you observe is that the attractive force is mostly driven by the quark contribution, while the repulsive force, while the attractive force comes from the gluons and is more wide range, long range. Then you can.
Could you remind me the plots? It's hard to see the top and the bottom.
So this is the radial pressure. If you look at the radial direction, and this is the tangential pressure. So orthogonal to the radial direction. Yes, R and T. So it's not very clear.
So tangential pressure, yes, this way is negative.
It's negative outside this. So this, and then we go back to this, is actually surface tension if you integrate it. So you can express the radial and tangential in terms of the isotropic pressure and the pressure anisotropy. I don't have much time here to discuss. So now we can focus on the question of I will call hydrostatic equilibrium, which is nothing as the statement that for these forward matrix elements, which are considered in the bright frame, which means that they are time independent, we can think of them as average over time. Only the stress part of the H2 tensor is conserved by itself. So from that, you infer that relation that relates essentially the derivative of the radial pressure to the pressure anisotropy. And this expression is already well known in the case of gravity, where they have an extra terms which is associated with external gravitational field that we don't have in our case here. So from that simple hydrostatic equilibrium equation, you can infer many relations. And one of them is very well known, which is the Van-Loon relation, which tells you that the isotropic pressure integrated over all space should give 0. That's what we have indeed. The positive pressure is the core of the nucleon is compensated by the negative pressure of the outer part. And the pressure anisotropy, if you integrate over a slab of matter, this defines the effective surface tension of your system. This you can see it because from that relation you can relate the pressure, the isotropic pressure at the center of the nucleon to a certain function of the pressure anisotropy. So if you are looking at ordinary liquids, the density is essentially constant, and there's a big change only at the interface with a different medium, like air or something like this. So actually there is also anisotropy in this ordinary matter, but it's only on a very thin layer, which is usually modeled by an infinitely thin, that we have a delta function in the direction which is normal to the interface. And the coefficient is what we call the surface tension. So if you plug this in the expression, you recover the well-known expression from the Young-Laplace relation between the pressure inside the bubble and the surface tension. So all this is there. That's why it's very interesting and exciting. So now, last point, I wanted to compare with neutron stars. So as you know, neutron stars are very specific stars which can be formed at the very end of massive stars after the supernova explosion. It can give neutron stars, it can give white stars, many things. All this very compact environment are called globally compact stars. In those objects, astrophysical objects, that's where in the universe, except for the nucleon, you will observe the highest energy densities and the strongest gravitational field. And it's a very nice environment because you can test many things, especially test the limits of our knowledge of nuclear matter under extreme conditions, and also to see whether general relativity still holds in those environments, because so far general relativity has been a big success, but has been only tested for relatively weak gravitational fields. For strong gravitational fields, we have no idea whether it's the ultimate theory. And there are many arguments that now are pointing towards that inside the nucleon, we can have many structures. Essentially, the outer structure is pretty well described by ordinary nuclear matter. As you go inside, you are going further and further outside the regime where you can use ordinary nuclear physics. Relativistic corrections becomes important. So that's why people are looking at the equation of states for ion-ion collision. And maybe at some points, we may have some quark matter over here. So you can compare the mass. So the neutron star has a mass of typical 1.4 solar mass, radius about 10 kilometers, and the average density, density is 3 times the average nuclear density. So it's extremely dense system, and gravitation is also extremely high. If you compare with the numbers you get for a proton, well, the density is here about 2.4 for the average. So it's not too far. Maybe we can say something about it. So that led me to the idea that maybe if we study the energy molecular density of the nucleon, we can, of course, write the relation between the pressure and the energy. Then you can compare for the total, the isotropic pressure, the radial pressure, and the tangential pressure have this relation. And if you report that in a chart that you find for the constraints equation of state using also the recent gravitational wave observations, what we observe is that what we have with the simple model is we are living in that region. So definitely, maybe we could say something about what's happening inside the neutron star. And you can do this separately for quarks and gluons. So that would be an interesting application of these kind of studies. And going the other way around, people have studied a lot stability constraints of neutron stars. So from these analysis, maybe we can also have new constraints on the structure of the nucleon. For example, what we need, for example, is that the energy pressure should be finite, the pressure isotopy should vanish, the radial and energy density should be always positive with a negative slope. Then also we have constraints on the velocity of sound, especially it should be smaller than the speed of light. There are also energy conditions which are used in many theorems related to black holes. So it's not easy to satisfy all those constraints at once. So that's why when you do, for example, GPD phenomenology, which is connected to gravitational form factors, this may give further constraint on your GPDs. So you may really learn something interesting from these stability conditions.
Well, the interesting thing about neutron stars is that, you know, because it's very stiff. Okay?
Yes.
If you change the density by a little bit, the energy density really changes a lot.
Exactly.
So the question is, can you tune the size of your nucleon so that you can see what the energy density?
So far I haven't tuned at all the size of the nucleon, but I say just with what the little I know and with the simple model we used, just to have a rough idea of what we can get. Because I could have been totally off. That's just what I get, and also observe a pretty stiff relation. And the stiff relation is very important because that's the one that you need in order to describe the mass.
How do you change the baryon density? You're looking at the local density inside the object?
Inside the proton, yes. Yes. With the gravitational form factor, with the T dependence, and this gives you information about the spatial distribution of energy and pressure inside the proton itself. So I'm now at the end of my summary, as with my presentation. Another question. It's good. So many of the features that we're interested are encoded in the geometric tensor. So I think it's a very nice object. We have to focus to have a global picture of all those aspects. The energy density and pressure are really high inside the proton. There are lots of relativistic effects, and we have a large anisotropy. It's very interesting because what we obtain, for example, for the equation of state, is in the same ballpark as situation that is thought to be encountered inside neutron stars. We may say something about it. So it would be nice to investigate further on possible relation between these. And of course, the EIC will play a key role because definitely we need the nucleon contributions, which are not so well constrained. We need to have the imaging, and of course, going into different environments for nuclei will be important. Very last slide, I would like to invite you all to a meeting next year in École Polytechnique, which is mostly a theoretical workshop, but also we have usually experimentalists to present the physics that recently has been mostly related to looking at the proton from the point of view of the lab front, of the nucleon structure, JLab, compass, lyric, some physics is presented there. So you are very welcome. I hope to see you there. Thank you very much.
On practical questions, check with Fun